Welcome! In this video, we will explore key concepts in real polynomials, essential for the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to, first, analyze the end behavior of polynomial graphs based on their degree and leading coefficient. Second, find the exact zeros of cubic and quartic polynomials using a combination of technology and algebraic methods. And third, solve polynomial inequalities, both algebraically using sign diagrams and graphically. Let's begin by understanding the general form of a polynomial. A general polynomial, which we can call p of x, is defined as p of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1, and so on, down to a sub 1 times x plus a sub 0. Here, n is a non-negative integer representing the degree of the polynomial, and a sub n is the leading coefficient, which cannot be 0. The degree, n, is the highest power of x, and the leading coefficient, a sub n, is the coefficient of that highest power. The end behavior of a polynomial graph, that is, what happens to the graph as x approaches positive or negative infinity, is determined solely by its degree and the sign of its leading coefficient. Let's analyze this behavior by considering two cases, when the degree is even and when it is odd. First, let's look at polynomials with an even degree, like a quadratic or a quartic. For an even degree polynomial, the end behavior is the same on both sides. The graph either goes up on both the left and right, or down on both the left and right. The direction depends on the sign of the leading coefficient, a sub n. If the leading coefficient is positive, the graph rises on both ends. Think of a standard parabola, y equals x squared. As x goes to infinity or negative infinity, y goes to positive infinity. If the leading coefficient is negative, the graph falls on both ends. Consider y equals negative x squared. As x goes to infinity or negative infinity, y goes to negative infinity. So for even degree polynomials, the ends of the graph always point in the same direction. Now, let's consider polynomials with an odd degree, such as a cubic or a quintic. For an odd degree polynomial, the end behavior is opposite on each side. The graph will go up on one side and down on the other. Again, the direction is determined by the sign of the leading coefficient. If the leading coefficient is positive, the graph falls on the left and rises on the right. Think of y equals x cubed. As x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. If the leading coefficient is negative, the graph rises on the left and falls on the right. Consider y equals negative x cubed. As x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. This opposite end behavior for odd degree polynomials has a very important consequence. It guarantees that the graph must cross the x-axis at least once. This means every real polynomial of odd degree must have at least one real zero. Let's move on to finding the zeros of polynomials. A zero of a polynomial p of x is a value of x, for which p of x equals 0. Graphically, these are the x-intercepts. For cubic and quartic polynomials, finding zeros can be challenging. We often use a two-step process. First, we use technology, like a graphing calculator, to find an approximate real zero. Second, we use that approximation to find an exact rational zero, and then use algebraic methods to find the remaining zeros. Let's work through an example. We'll find the exact zeros of p of x equals 3x cubed minus 14x squared plus 5x plus 2. Our goal is to find the exact zeros of this cubic polynomial. Step 1. Use technology. If we graph this function, we can see that it crosses the x-axis at approximately 0.6666667. This decimal approximation is a strong hint that the exact zero is the rational number 2/3. Step 2. Use algebra. If x equals 2/3 is a zero, then by the factor theorem, by 2/3 must be a factor. To avoid fractions, we can multiply by 3 to get the factor, 3x-2. So we know that 3x negative 2 is a factor of our polynomial. Now we can write the polynomial as a product of this linear factor and a quadratic factor, We can find the coefficients of the quadratic factor x squared plus ax minus 1 by equating coefficients. Let's compare the coefficients of x squared on both sides. On the left, it's minus 14. On the right, it's 3a minus 2. Setting them equal, we get 3a minus 2 equals negative 14. Solving for a, we find that a equals negative 4. We can verify this by equating the coefficients of x. On the left, it's 5. On the right, it's negative 3 minus 2a. Substituting a equals negative 4, we get negative 3 minus 2 times negative 4, which is negative 3 plus 8, which equals 5. This confirms our value for a. So our polynomial is now factored as p of x equals 3x minus 2 times x squared minus 4x minus 1. The zeros are found by setting each factor to 0. The first factor gives us x equals 2/3. For the quadratic factor, we use the quadratic formula. Using the formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, we get x equals 4 plus or minus the square root of 20 all over 2. We can simplify the square root of 20 to 2 times the square root of 5. So x equals 4 plus or minus 2 times the square root of 5 all over 2. Dividing by 2, we get x equals 2 plus or minus the square root of 5. Therefore, the exact zeros of the polynomial are 2/3, 2 plus the square root of 5, and 2 minus the square root of 5. We have successfully found all three exact zeros of the cubic polynomial. Let's try another example, this time with a quartic polynomial. We'll find the exact zeros of p of x equals x to the 4th minus 4x cubed plus 3x squared plus 2x plus 7. Our goal is to find the exact zeros of this quartic polynomial. The problem statement gives us a crucial piece of information. X squared plus x plus 1 is a factor. This means we can write our quartic as the product of this quadratic factor and another quadratic factor. We'll use the method of equating coefficients to find a and b. Let's start with the constant term. On the left, it's 7. On the right, it's 1 times b. So b must be 7. Next, let's equate the coefficients of x. On the left, it's 2. On the right, it's 1 times a plus 1 times b. So 2 equals a plus b. Since we know b is 7, we have 2 equals a plus 7, which means a equals negative 5. We can verify this with the x squared term. On the left, it's 3. On the right, it's 1 times b plus 1 times a plus 1 times 1. That's b plus a plus 1. Substituting our values, we get 7 minus 5 plus 1, which is 3. This confirms our values for a and b. So our polynomial is factored as p of x equals x squared plus x plus 1 times x squared minus 5, x plus 7. Now we need to find the zeros of each quadratic factor. Let's start with the first one. For x squared plus x plus 1 equals 0, the discriminant, b squared minus 4ac, is 1 squared minus 4 times 1, which is negative 3. Since the discriminant is negative, this quadratic has no real zeros. Its zeros are complex. Now for the second factor. For x squared minus 5x plus 7 equals 0, the discriminant is negative 3. Again, this quadratic has no real zeros. Since neither quadratic factor has real zeros, the original quartic polynomial has no real zeros. This means its graph does not intersect the x-axis at all. We have shown that the graph of f of x does not meet the x-axis. Next, let's tackle polynomial inequalities. The process is very similar to solving polynomial equations. Our objective is to solve inequalities of the form p of x is greater than or equal to 0, or p of x is less than 0, and so on. The key steps are to first rearrange the inequality so that one side is 0, then find the zeros of the polynomial, and finally use a sign diagram to determine the intervals where the inequality holds. Let's solve the inequality. X cubed plus 6 is less than or equal to 4x squared plus 9x. We need to find the values of x that satisfy this inequality. Step 1. Rearrange. We move all terms to the left-hand side to get a polynomial inequality. This gives us x cubed minus 4x squared minus 9x plus 6 is less than or equal to 0. Step 2. Find the zeros of the polynomial p of x equals x cubed minus 4x squared minus 9x plus 6. We can use technology to find a rational zero. A graph shows a root at x equals negative 2. Since x equals negative 2 is a zero, x plus 2 is a factor. We can now factor the polynomial. By equating coefficients, we find that x cubed minus 4x squared minus 9x plus 6 equals x plus 2 times x squared minus 6x plus 3. The zeros of this polynomial are negative 2, and from the quadratic formula, 3 plus or minus the square root of 6. Step 3. Create a sign diagram. We place the zeros on a number line in increasing order. The zeros are negative 2, 3 minus the square root of 6, and 3 plus the square root of 6. Now we test a value in each interval to see if p of x is positive or negative. For example, if x is less than negative 2, say x equals negative 3, p of negative 3 is negative. If x is between negative 2 and 3 minus root 6, say x equals 0, p of 0 is positive, and so on. The sign diagram shows us where the polynomial is positive and where it is negative. We are looking for where p of x is less than or equal to 0. This occurs in the intervals where the sign is negative. The solution is x is less than or equal to negative 2, or x is between 3 minus the square root of 6 and 3 plus the square root of 6, inclusive. An alternative way to solve inequalities is graphically. This method is particularly useful when exact zeros are difficult to find. Let's solve the inequality 2x cubed minus 7x squared plus 5 is greater than x minus 5. We want to find where the cubic function is above the linear function. Step 1. Define two functions. Let y1 equal the left side and y2 equal the right side. So we have y1 equals 2x cubed minus 7x squared plus 5, and y2 equals x minus 5. Step 2. Graph both functions on the same set of axes using technology. We can see the cubic curve and the straight line intersecting at 3 points. Step 3. Find the points of intersection. Using the calculator's intersect function, we find the approximate x-coordinates of these points. The intersections occur at approximately x equals negative 1.10, x equals 1.44, and x equals 3.16. Step 4. Interpret the graph. We are looking for where y1 is greater than y2, which means where the graph of the cubic is above the graph of the line. Looking at the graph, the cubic is above the line in two intervals, between the first two intersection points, and to the right of the third intersection point. Step 5. Write the solution using the x-coordinates of the intersections. The solution is x is between negative 1.10 and 1.44, or x is greater than 3.16. This graphical method provides a quick way to find approximate solutions to inequalities. Let's work through a more complex problem involving a quartic function and its graph. The graph shows the height, h, of a roller coaster as a function of the horizontal distance, x. The equation is given in factored form. The equation is h of x equals negative x times x minus a squared times x minus b, all divided by k. Part A asks us to use the graph to find the values of a and b. We need to find the values of a and b from the graph. The zeros of the function are the x-intercepts. From the equation, the zeros are x equals 0, x equals a, and x equals b. The graph shows x-intercepts at x equals 0, x equals 100, and x equals 200. Notice that the graph touches the x-axis at x equals 100 and turns around. This is characteristic of a repeated root, or a root with an even multiplicity. In our equation, the factor x minus a is squared, indicating a repeated root at x equals a. Therefore, we can conclude that a must be 100. The other root, b, must be 200. So the equation is now h of x equals negative x times x minus 100 squared times x minus 200, all divided by k. This is our updated equation. Part B asks us to find the value of k, given that the height is 4 meters after traveling 100 meters. We need to find k using the point 104. Let's substitute x equals 100 into our equation for h of x. H of 100 equals negative 100 times 100 minus 100, squared times 100 minus 200, all divided by k. The term 100 minus 100 is 0, so the entire numerator becomes 0. This means h of 100 is 0, not 4. This is a contradiction. The graph clearly shows the roller coaster is at height 0 at x equals 100. The problem statement is incorrect. Let's assume the problem meant to give a different point, for example, the peak height. The graph shows a peak height of 40 meters at x equals 50. Let's use this point instead. Let's assume the problem meant h of 50 equals 40. Substituting x equals 50 and h of x equals 40 into the equation. 40 equals negative 50 times 50 minus 100 squared times 50 minus 200, all divided by k. Let's simplify the numerator. This becomes negative 50 times negative 50 squared times negative 150. Negative 50 squared is 2,500. So we have negative 50 times 2,500 times negative 150. Multiplying these numbers gives us 18,750,000. So 40 equals this value divided by k. Solving for k, we get k equals 468,750. Part C asks for the height after traveling 150 meters. We need to find h of 150. We substitute x equals 150 into our equation with the value of k we just found. H of 150 equals negative 150 times 150 minus 100 squared times 150 minus 200, all divided by 468,750. Simplifying the numerator. This is negative 150 times 50 squared times negative 50. This simplifies to 18,750,000. Dividing gives us a height of 40 meters. This matches the graph, which shows a height of 40 meters at x equals 150. Let's conclude with a quick review of the key concepts we've covered. We started by analyzing the end behavior of polynomials, which is determined by the degree and leading coefficient. We then learned how to find exact zeros of cubic and quartic polynomials by combining technology and algebraic methods like equating coefficients. Finally, we explored how to solve polynomial inequalities using sign diagrams or by comparing graphs. These skills are fundamental for understanding and working with polynomials at the HL level. Now let's move on to some practice questions. Here are 5 practice questions designed to test your understanding of these concepts. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the exact zeros of p of x equals 2x cubed minus 3x squared minus 4x minus 35. Question 2. Solve the inequality x cubed plus x squared minus 11x minus 15 is greater than or equal to 0. Question 3. Find the equation of the cubic polynomial whose graph passes through the points negative 2, 0, 0, 12, and 3, 0. Question 4. Find the sum and product of the roots of 3x to the 4th minus 4x cubed plus 3x squared plus 8 equals 0. And question 5. Show that x equals 1/4 is the only real solution of 4x cubed minus 13x squared plus 15x minus 3 equals 0. Take your time to solve these. When you're ready, let's go through the solutions. Let's review the solutions to the practice questions. For question 1, the exact zeros are 3.5 and negative 1 plus or minus I times the square root of 3. To get this, you would use technology to find the real zero at x equals 3.5. This means 2x minus 7 is a factor. Dividing the cubic by this factor gives the quadratic 2x squared plus 4x plus 10. The zeros of this quadratic are complex. For question 2, the solution to the inequality is x is greater than or equal to 3, or x is between negative 3 and negative 1, inclusive. You would find the zeros of the cubic, which are negative 3, negative 1, and 3. Then, you would use a sign diagram to find the intervals where the polynomial is non-negative. For question 3, the equation of the cubic is y equals negative 2 times x plus 2 times x minus 3 times x minus 1. The x-intercepts give us the factors x plus 2 and x minus 3. So the equation is y equals a times x plus 2 times x minus 3 times x minus c. Using the y-intercept, 0, 12, and another point from the graph, you can solve for a and c. For question 4, the sum of the roots is 4/3, and the product of the roots is 8/3. Remember the formulas for the sum and product of roots. For a quartic, ax to the fourth plus bx cubed plus cx squared plus dx plus e equals 0, the sum is negative b over a, and the product is e over a. For question 5, the only real solution is x equals 1/4. You would find the real 0 at x equals 1/4 using technology. This gives the factor 4x minus 1. Dividing the cubic by this factor gives the quadratic x squared minus 3x plus 3. The discriminant of this quadratic is negative, so it has no real roots. I hope this video has helped you deepen your understanding of real polynomials. Keep practicing these techniques to master them for your IB exams. Thank you for watching.